Good morning, welcome to today's lesson. Although you may be watching this at night, so good night. Welcome to today's lesson, 4.2, day 1. This is all about the mean value theorem. This is not a mean theorem. This is all about average value theorem for derivatives. Okay, this derivative, it's listed on page 196. You may need to look at your book for this a little bit, but here's what it says. If you have a function that's continuous, closed, and differentiable, then there's at least one point where the instantaneous rate equals the average rate. On the left-hand side of this formula, we have what's called the instantaneous rate or the derivative. Remember that rate of change is the derivative. The average rate of change on the right-hand side is just like the slope, just like we've taken slope for hundreds of years since we were wee tots in Algebra 1. Okay, this theorem makes sense. It says that if you have an average rate, like let's say you drive to school, you have an average rate of 40 miles per hour. Well, sometimes you're stopped and going 0. Sometimes you might be going 70 if you're on the highway, but maybe your average rate is 40. So that says that in between your drive to school, somewhere you hit the value of 40 at least once. And that's what this theorem says. It makes sense. All right, so let's do a couple of examples. All of these examples today are from your assignment. And there's a bunch of them. So anyway, this is number 6, page 202. Does this function satisfy the criteria for the mean value theorem, which I'm abbreviating MVT, for the MVT to apply? All right, so that means we ask ourselves, does it have a closed interval? Check. Is it continuous? Yes, natural log is continuous. Is natural log differentiable? Yes. Therefore, the answer is yes. There is a point on this curve where your derivative is going to equal your average. So we're going to use our trusty little equation. And we know the derivative of ln of x minus 1. The derivative of this is equal to 1 over x minus 1. Now we're going to plug in values. This is an interval, 2 to 4. So we're going to take the function at 4 minus the function at 2 divided by 4 minus 2 equals 1 over x minus 1, because that's the derivative. And actually we're looking for some value c. So let's just, to be cool, let's call this value c. It doesn't really matter, but that is the value you're looking for, okay? So let's see, this function at 4 is ln of 3 minus the function at 2 is ln of 1 over 2. Oh, my board. Okay, so let's continue on solving. We have 1 over c minus 1 equals ln of 3. Remember that ln of 1 is equal to 0. So we have ln of 3 over 2. Now, the way we can solve this is just cross multiply. That's what I would do. So ln of 3 times c minus 1 equals 2. This cross equals that cross. All right, now we have to distribute our ln3 to both of these. ln3 is just a number. So c ln of 3 equal, or minus ln of 3. That's 2. So we have 2, add ln of 3 to both sides. I'm doing a little algebra here. C ln of 3, and then we just need to divide both sides by ln of 3. And if you put that number in your calculator, divide by this, you get c is 2.82. That is the x value where your instantaneous rate of change equals your average rate of change using the mean value theorem. The next two examples are also in your assignment, and they are more physical interpretations rather than actual function interpretations. but we're still going to use the mean value period, mean value theorem, sorry. It takes 20 seconds for temperature to rise from 0 to 212 when a thermometer was taken from a freezer and placed in boiling water. Explain why at some interval the mercury was rising at exactly 10.6 degrees Fahrenheit. Okay, the reason, we're going to try to see if we can explain this using the MVT, the mean value theorem. If the mean value theorem holds true, this might work. So, what we're going to do is take the temperature 212 minus the temperature 0 and divide that by the end temperature minus the beginning temperature. Okay, so if we do that, we get 212, which is our function value at the end. 0 is our ending temperature. And we took 20 seconds to do that. 212 divided by 20 is, surprise, 10.6. And remember, this is degrees, this is seconds. So we have degrees Fahrenheit per second. All right, and using the mean value theorem, that is how we know that at some moment that temperature was 10.6 degrees. It makes sense. Here's another one, running a marathon. Show that the runner ran 11 miles per hour at least twice. This is number 14 in your assignment. We're going to use the same theory as the temperature. Our function at the beginning, this is the beginning minus the ending race, and what we use is miles per hour. So we have 26.2 miles is our ending part of the race. We started at 0 miles, and it took us 2.2 hours to do that. If we divide those two numbers, we get 11.909, and that is in miles per hour. And that says that this is our derivative or our rate of change. This is our average rate of change. And the question was, show that the runner ran 11 miles per hour at least twice. Well, if you start at 0 miles per hour, go up and you're going to go up to at least 11 and then come back down. You have to have run 11 miles at least twice, because we're going right here up to 12. So we go 0 up to 12-ish and then come back down. So there must be 2 times right here that we reach 11. Okay, so the runner had to be at 11 miles per hour at least twice, probably even more in real life. Okay, next problem. Next 2 problems, 53 and 56, also both on your homework assignment. All right, so we are going to check and see. This is just like the very first problem we did, both of these. The thing we need is the derivative right here, and because we're going to use our mean value theorem formula, derivative of cosine is negative sine of x. All right, that's what we put in over here. We're actually going to use negative sine of c, just so we can keep consistent with the c values. All right, we're going to put our function in at pi over 3 minus 0, and see how that works for us. Cosine pi over 3 minus cosine of 0. Okay, and we divide that by pi over 3 minus 0. So actually, I did more work than was required on this problem, because all they're looking for, this is one of those multiple guess jobbers, and all they're asking you for is what is the derivative at c. So whatever you get for this is going to be your answer, and you have to match it up with one of the answers in the book. Now this is how much work I should see for a multiple choice problem like that, by the way. All right, so we have 1/2 minus 1 on the top. We have pi over 3 in the denominator. So this problem asks us to do a little legal algebra. and calculate the actual fraction value, if you flip the guy and multiply, you get minus 3 over 2 pies. And that is your answer. Happens to be A. The next problem is number 56. It has the same sort of question. It says, oh, this one says, which one of these problems does not satisfy, no, it says, yes, which one does not satisfy the mean value theorem between -1 and 1? Okay, so A, I know sine is, and remember the 3 conditions, we don't actually need this here. The 3 conditions for the mean value theorem are continuous, that means, oh, whoops, sorry, US, and closed interval. Well, we already have the closed interval, so we don't even have to check that for everyone because they gave us the interval. And differentiable. Now here's what you look for in differentiable. Remember, there are 4 ways you can be not differentiable. If you have a cusp, if you have a corner, if you have any sort of discontinuity, okay, any one of the CON continuity. All right, and then last one is a vertical tangent. Okay, if you have any one of those 4 conditions, you are not differentiable. Okay, sine of x from -1 to 1 goes like this. It is differentiable everywhere. Cross A off the list. B is inverse sine of x. That just flips sine sideways. So that is also differentiable on that -1 to 1. X to the 5/3. Okay, so x to the 5/3 takes something to the 5th power and then takes the cubed root of it. And what's our next one? X to the 3/5. So D is one, though, that at x equals 0, we have a vertical tangent. Remember, it looks like this. You can go back in your notes and kind of look at the non-differentiable functions we had in chapter 3. So at n equals 0, this is not differentiable because it has a vertical tangent. X to the 5/3 kind of goes like this. It really doesn't have that kind of a vertical tangent like this one does. E, and you can check those out on your calculator as well, and also look back at the section in chapter 3. And then the last one is like x over x minus 2, and it has a, so these are all out. E has a discontinuity at 2, x equals 2, but our interval is just -1 to 1, so we don't worry about that one. And going back to inverse sine, remember inverse sine is only defined between -1 and 1. So also if you look back in section 1 of our book, it shows graphs of all the inverse sine functions and how we limit their domains. So sine of x inverse is also good. All right, it pays to know a little bit about your functions on this one. Okay, so that's it. So have a good day, and that's section 4.2, day 1.